Hello friends, so today we are going to solve the you can say this is part 4 and the last part for the year 2020, and in this we are going to solve 7 questions, and all these 7 questions are from the advance. In the first 3 parts we solved for the year 2020, but the questions were only from the mains one. So this is the final part with 7 questions, and all questions are from the advance. So the first question: a uniform electric field E given as minus 400 square root of 3 y unit vector Newton per coulomb is applied in a region. A charged particle of mass m carrying positive charge q is projected in this region with an initial speed of 2 into square root of 10 into 10 is power 6 meter per second. Okay, so this is 2 meter per second. This particle is aimed to hit a target T, which is 5 meter away from its entry point into the field schematically in the figure. Take q by m as 10 raised to power 10 coulomb per kg. Then we have to find out the time and the angle of the projection. So basic figure is given to us. We can assume that this target or initial direction of the projection is with respect to x-axis, and this is our y-axis. From here the charged particle is making an angle of theta with our x-axis, and it is going to hit the target T, and we have to find out this value of theta. So in this case it's a more or less a combination of the basic electrostatic as well as the projectile motion. So from here we can, from the figure itself, it's clear that the net vertical displacement, or we can say simply vertical displacement of the charged particle, is equal to 0. So we have to keep this in mind. So first of all we are going to find out the acceleration due to the electric field. Okay, then we are going to use the projectile motion equation. So we can say acceleration due to electric field, and we can say that the force experienced by the electric field due to electric field is our q multiplied by electric field. Then this force due to electric field we can write as acceleration to mass is equal to q upon q into E, so which gives us acceleration is equal to q multiplied by E divided by m. So we can just substitute the value. We can say acceleration is equal to q is q upon m is given. Q upon m is 10 raised to power 10, and electric field is also given to us as minus 400 square root of 3. So from here we get the acceleration will be equal to minus 4 into 10 raised to power 12 and multiply by square root of 3 meter per second square. And in the figure itself we are given that the initial velocity u is making the angle theta with the horizontal. So we can divide this u into 2 components. So this is our x-axis, initial velocity u making angle of theta. So one component will be our u of x and the other component will be our u of y. So we are given that initial velocity is at angle theta with x-axis. Therefore, we get that our horizontal component which we called as u of x will be equal to u cos of theta, and we have vertical component that we called as u of y is our u sine of theta. And let us suppose that this object is at a distance x. Okay, later we can just substitute the value. So if this is at a distance of x, so x is basically a range of this charged particle, and this is along the x-axis. And if we say that for time of flight, if taken as small t, therefore we can write that the range which is assumed over here as x will be equal to the horizontal velocity multiplied by t. So we get this as u cos of theta multiplied by t. And the vertical displacement is 0 in this case. Net vertical displacement is 0 in this case. So we can say that net vertical displacement, if we assume that is our y, then this y is equal to 0. And we can write the equation for this y by using the equation of kinematics. We can say our y is equal to our vertical velocity v of t plus half a t square, and this will be equal to 0. We substitute value of u of y as well as our acceleration, and this gives us u of y was our u sine of theta multiplied by t, and let me write. So we get this as our u sine of theta multiplied by t plus half. Acceleration we found out is our minus 4 square root of 3 into 10 raised to power 12 t square is equal to 0. And one of the factor will be equal to t. Obviously that cannot be equal to 0. Therefore the other factor, we can write this as our u sine of theta is equal to, here this 4 goes by 2, this comes as 2 root 3 into 10 raised to power 12 t. And from the horizontal, let us suppose this is our equation 1. So we can say from equation 1, equation 1, we know that our x is equal to u cos of theta multiplied by t. X is given to us as 5, so this is equal to 5. Okay. Therefore, we can write that the value of t will be equal to 5 u cos of theta. And let us suppose this is our equation number 2. So we are going to use the value of t we just calculated in equation 2. In equation 2, we get u sine of theta is equal to 2 root 3 into 10 raised to the power 12 multiplied by 5 u cos of theta, and this comes as u square sine theta into cos theta, u square sine theta into cos theta is equal to, this comes as 10, so it comes as 10 raised to the power 13 square root of 3. And we can convert this sine theta into cos theta by a double angle, or we can say half angle. So we can write this as 1 by 2 u square sine of 2 theta is equal to 10 raised to the power 13 square root of 3. And from here we can write that sine of 2 theta will be equal to 2 into 10 raised to the power 13 square root of 3 divided by u square. And the velocity is, initial speed is given to us 2 square root 10 raised to the power 10 into 6, 10 raised to the power 6. So we substitute that, we get that our sine of 2 theta is equal to, this is 2 into square root of 3 into 10 raised to the power 13, and u square is our, u is our 2 square root of 10 into 10 raised to the power 6, and this comes as whole square. So we get this as our 2 square root of 3 into 10 raised to the power 13, and we have this as 4 into 10 into 10 raised to the power 12. So therefore we get this as, this comes at 13, 13 goes 13, 4 goes by 2. So we are left with that our sine of 2 theta will be equal to square root of 3 divided by 2. Or we can say that our from here we can get the two values of theta, 2 theta first of all. So we get 2 theta is equal to, either it will be over 60 or it will be 120. So from here we get our theta will be either equal to 30 or it will equal to 60. Okay. So the value of theta is either 30 or is equal to 60. So obviously option A is not correct and option B is correct, because it is saying both 30 and 60. So we can easily find out that option B is correct. Option B is correct. And time of flight we already know, we already got the formula for that. And time of flight, that is our t is equal to 5, we have this as u cos of theta. And let's try for both value of theta. So first is our theta is equal to 30, and for cos of 30 is going to give us square root of 3 divided by 2. This is a t is equal to 5, u is our 10 square root 10 is to power 6, and this comes as square root of 3 divided by 2. So here 2 goes with 2, and this comes as square root of 30. So we get our t is equal to over 5 divided by square root of 30, and ten is to power 6, and we can write this as square root of 25 divided by 30 and microsecond. So here this goes by 5 and goes by 6, which comes as square root of 5 upon 6 microsecond. And let's find out for other value of t, sorry not t but theta. So other value of theta is our 60. We get cos of 60 1 by 2. This gives t is equal to 5 2 square root of 10 raised to power 6 into 1 by 2. And once again 2 and 2 cancels out. So we are left with only that our t is equal to 5 upon square root of 10 microsecond. This can be once again written as 25 upon 10 square root micro, and this goes by 5 and this goes by 2. So we get this as 5.2 microsecond. So the option is, so option C is correct, but option D is incorrect. So we have option C is correct. C is correct. Next question. It states that one end of a spring of negligible unstretched length and spring constant K is fixed at the origin O, 0, 0, a point particle of mass m carrying a positive charge Q is attached at its other end. The entire system is kept on the smooth horizontal surface. When a point dipole P pointing towards the charge Q is fixed at the origin, the spring gets stretched to a length small l and attains a new equilibrium position as shown in the figure. If the point mass is now displaced slightly by delta L, which is much smaller than L, from its equilibrium position and released, it is found to oscillate at a frequency of 1 upon delta square root of K divided by M. The value of delta is. Basic figure is given to us, and we are given that we have a spring of which is of stretched length is L. Okay. And dipole is placed at the origin pointing toward the charge Q, which is placed at the other end. Okay, and we have to keep in mind that it is in equilibrium. So first of all, we are going to find out the force between the dipole, point dipole and point charge. Okay. And under equilibrium condition, this force will be equal to the restoring force, because the dipole is going to push the charge towards right and dipole, our spring is going to restoring force toward the left, and in equilibrium these both should be equal. Okay. So we are going to find out the force between point dipole and point charge. Force between point dipole and point charge. Let us call this as our Fe. So first of all, we are going to find out our electric field. So we can say the electric field at a distance r from a point dipole P, from a point dipole P, that is our electric field, will be equal to 1 upon 4 pi epsilon naught. This comes as twice P divided by our r cube and multiply by the r unit vector. So therefore we can find out the force now. Force on the charge Q. Charge Q, which we just called as our Fe, will be equal to Q times electric field. So we substitute value of formula for the electric field. We get this as force due to electric field is equal to 1 upon 4 pi epsilon naught. This comes as 2p times q r cube, and we have a r unit vector. Okay. And this will be obviously repulsive force. Repulsive force. And in equilibrium condition, you can say the restoring force balances the Fe. Restoring force balances the repulsive force. Repulsive force. So our restoring force will be equal to our K times L, which will be equal to 1 upon 4 pi epsilon naught 2pq, and the distance in this case is L, so we can going to replace our R by L, so this comes as our L cube. So this gives us spring constant K will be equal to 1 upon 4 pi epsilon naught, and this is our 2pq L raised to power 4. Let us call this as equation number 1. Now it is being displaced by a small amount, that is delta L. So we are going to find out the effective force for the small displacement. Effective force for small displacement, which is given as delta L, but much smaller than L. And so the new length of spring will be equal to L plus delta L. Therefore, our spring force let us call this as our Fs will be equal to minus K L plus delta L. Similarly, we are going to find out the electric force. And let us call this as Fe prime will be equal to 1 upon 4 pi epsilon naught, and this is 2pq divided by L plus delta L and whole cube. So we can find out the net storing force about equilibrium. Net storing force about equilibrium and we can write this as F net will be equal to minus K L plus delta L plus 1 upon 4 pi epsilon naught to PQ L plus delta L and whole cube. And at equilibrium, we can say the two forces should balance out each other. So we can just expand this denominator of L plus delta L whole cube. Okay. So we can say that 1 upon L plus delta L whole cube, it can be approximately written as, if we take our L as common, so this comes as 1 upon L cube 1 minus 3 delta L upon L. So we substitute value of into the net force, so we get our F net will be equal to minus K L plus delta L plus this comes as 2pq upon 4 pi epsilon naught L cube times 1 minus 3 delta L upon L. But we just found out that at equilibrium the KL is equal to this equation. So we simply substitute it. So we can say that at equilibrium, let me write this as equation 1. So from equation 1, we have that our KL is equal to 2pq divided by 4 pi epsilon naught and L cube. And we can write our F net will be equal to minus KL minus K into delta L plus KL and minus 6 PQ divided by 4 pi epsilon naught, and we have here L4 multiplied by delta L. and this gives us KL and KL cancels out, so we get this as minus K delta L minus 6 PQ 4 pi epsilon naught L raised to power 4 and multiply by delta L. So we can simply take minus as common and this comes as plus, and we can also take delta L also common. So we get this as K plus this equation, and we just found out value of K also. Let us call this as equation number 2. So from equation 2, we know that value of K is equal to 2 PQ upon 4 pi epsilon naught and L raised to power 4. Therefore, if we multiply both sides by 3, we get this as 3K is equal to 6 PQ 4 pi epsilon naught L raised to power 4. Now we can easily solve our Fnet. Fnet is equal to minus K plus 3K multiplied by delta L. So we get our Fnet is equal to minus 4K times delta L. So this is nothing but our equation for SHM. Net restoring force is proportional to the delta of L, which normally we represent as a X. So from here we can say our K effective will be equal to 4 times K. Therefore, we can write our angular frequency that is our W is equal to K effective divided by M and its square root. So we can write this as 4K upon M and its square root, which comes as 2 square root of K upon M. But we are given that our frequency is 1 upon lambda square root K upon M. So if we make 1:1 comparison, we can say our delta is equal to 1 upon 2. Now this is if we are asked for the angular frequency. But if we ask the linear frequency, that is F, so we can also say that we know that our K effective is our 4 times K. So based on this, we can write our time period T will be equal to, this is 2 pi, and we have M upon K effective. K effective is 4 times K. So this comes as 2 pi upon 2, and we have this as M upon K. So 2 goes with 2, and from here we can write our F is equal to 1 upon pi square root of K upon M, and which is given as 1 upon delta square root of K upon M. This gives us the delta is equal to pi. So depending upon whether it is a linear frequency or angular, we can just easily find out. And yes, so this value of lambda will either equal to 1 by 2 or this will be equal to pi. Next question. We are given that a circular disk of radius r carries surface charge density sigma r, sigma naught 1 minus small r divided by capital R, where sigma this rho naught is a constant and r is the distance from the center of the disk. Electric flux through a large spherical surface that encloses the charged disk completely is phi naught, and electric flux through another spherical surface of radius r by 4 and concentric with the disk is phi. Then the ratio of phi naught upon phi is. So we are given that we are having a disk, and let us draw an approximate figure. So we are having a disk whose radius is capital R. So this is a center and its radius is given as capital R, and we are having a, let us consider a, you can say, small disk which is concentric and at a distance of r from the center, and its thickness is suppose dr. So we are given that for the outer disk, okay, so for the outer disk we are given that the density is our 1 minus r upon capital R, okay, and the small disk which we consider, that is of thickness dr, the charge on it, let us suppose dq. Then this dq will be equal to our the charge density. Let me write this here. Consider a small portion of thickness dr at a distance r from the center. At a distance r from the center. Therefore, the charge on the charge which we said is our dq, then this dq will be equal to sigma naught 1 minus r upon capital R, and we have this as 2 pi r multiplied by dr. So this is the small charge, and we are going to find out the ratio of their respective fluxes. Okay. So obviously we are going to use our Gauss law. So we can say from Gauss law which says that electric flux through a closed surface depends only on the net charge enclosed. Only on net charge enclosed, which we can write that our phi is equal to charge enclosed divided by epsilon naught. So we can just write the ratio. So therefore ratio for the whole one is our phi naught, for the smaller portion is our phi. So this comes because epsilon naught is going to cancel. So we are going to get, because this phi naught is for the entire disk, so this we can write as charge total, and in the numerator will be our charge for the value of r, which is smaller than r by 4. So let's find out the total charge on the disk, because we are given the charge density. Total charge on the disk and we can write that our charge total will be equal to, and we can just use, we can say integrate it over the polar coordinates. So we are going to get this as zero to 2 pi, that's our theta, and our radius is from 0 to capital R. We have our charge density multiplied by R, and this is our dr and our d theta. Okay. So we can just make minor adjustment here. We can write, because the outer integral is of theta and internal one is with respect to our small r. So for the outer we can write this as theta is equal to 0 to 2 pi, taking derivative of theta outside, and then we can write this as r is equal to 0 to capital R, and we substitute value of our this charge density, which comes as sigma naught and 1 minus r upon capital R multiplied by r and dr. Now we can just simply integrate it, and so for this integration, this is our d theta will be automatically our theta, so we can substitute the limits. So this comes as 2 pi minus 0, which is our 2 pi. So this comes as 2 pi, and from the inner integral we can take this will be our constant, and we have our 0 to r 1 minus small r square upon capital R, or here we can write r also, and d of r. So if we integrate it, we are going to get this as 2 pi naught, and we have this as r square by 6, and this 6 goes by 3. So we get our charge total will be equal to pi sigma naught r square and divided by 3. So we found out one part. Now we are going to find out for the other part, that is the smaller one, when r is equal to capital R by 4. So you can say charge inside the radius small r, which is equal to over r by 4. So for that we can say our charge small r is less than r by 4 is equal to the angular will be same, that is for this portion it will be same, and it will be giving us this 2 pi, and sigma naught will be from the other integral. So this will be coming as same 2 pi sigma naught and we get this as 0 to r by 4 r minus r square by capital R, and this is our dr. So from here we get this will be equal to 5 pi sigma naught r square 96. So this is a charge for our r which is less than r by 4. Now we can just take the ratio which is required. So we get our phi naught upon phi is equal to, we have our pi sigma naught and r square by 3, and we have this as 5 pi sigma naught r square by 96. So this pi this sigma naught r square cancels out, and this comes as our 96 divided by 5 multiplied by 3. 5 multiplied by 3, and which gives us 32 divided by 5. So this is our ratio of their fluxes, 32 upon 5. Next question. We are given that two large circular discs separated by a distance of 0.01 meter are connected to a battery via a switch as shown in the figure. Charged oil drops of density 900 kg per meter cube are released through a tiny hole at the center of the top disc. Once some oil drops achieve terminal velocity, the switch is closed to apply a voltage of 200 volt across the disc. As a result, an oil drop of radius 8 into 10 to the power minus 7 meter stops moving vertically and floats between the disc. The number of electrons present in this oil drop is, neglect the buoyant force, take the acceleration due to gravity as 10 and the charge on electron as 1.6 into 10 to the power minus 19. So in this case, it is a simple case of, you can say, we have two discs. So the force in the downward direction is balanced by the force which is upward direction, because it states that it stops moving vertically and floats. So this is the entire premise of this question, or we can say net vertical force is 0. So we can say our oil drops floats. Our oil drop floats, which tells us net vertical force is 0. Net vertical force is 0. So obviously in the downward direction we are going to have a mg, that's the weight. Upward we are going to have a electric force. So we can simply write force acting on the top. Acting on the drop. Our first force is weight of the drop. Weight of drop, which will be in downward direction. Let us call this Fg, which will be equal to mg. And mass we can just write in the form of the density, that is about 4 by 3 pi r cube rho multiplied by g. And next is electric force, which will be acting in the upward direction. Let us suppose our Fe, once again it will be Q multiplied by E. and our electric field is nothing but our applied voltage and divided by distance. So this comes as Q times V and divided by D. So at equilibrium, Fg is equal to our Fe. We simply write the formula. Fg was our 4 by 3 pi r cube rho times G is equal to our QV divided by D. And from here we are going to find out our charge Q. And we can say our charge Q will be equal to 4 by 3 pi r cube rho, this is our G, D upon V. Everything is given to us, we simply substitute them. We get our Q is equal to 4 by 3 pi, and we have r cube, that is 8 into 10 to the power minus 7 whole cube, and density is given 900, multiply by distance between the plates is 0.1 and applied voltage is 200. So we get this value of charge will be approximately equal to 9.65 into 10 to the power minus 19 coulombs. Now it is quite easy. We know that the N multiplied by our quantization of charge, N into E, is equal to total charge Q, or we can say N is equal to Q upon E, which comes as 9.65 into 10 to the power minus 19, 1.6 into 10 to the power minus 19. Here 19 and 19 cancels out, and this comes approximately equal to 6. So we have 6 is our number of electrons. Next question. We are given that a point charge Q of mass m is suspended vertically by a string of length L. A point dipole of dipole moment P is now brought towards Q from infinity so that the charge moves away. The final equilibrium position of the system, including the direction of the dipole, the angles and the distances, is shown in the figure. If the work done in bringing the dipole to this position is n into mgh, where g is the acceleration due to gravity, the value of n is. Note that for 3 coplanar forces keeping a point mass in equilibrium, F is same for all the forces, where F is any one of the forces and theta is the angle between the other two forces. So basic figure is given to us that initially, this is a final figure basically given to us. So initially what happens, we are having a charge Q which is somewhere here, that is quite vertical, and we are bringing a dipole, point dipole P in this, and this is fixed at this particular end. So as the dipole is coming close to this, the charge will be pushed along in this direction. So automatically, so if this is our horizontal plane, then the final position of the charge is given to us as this P takes the position of the dipole, the position of the charge. So now the dipole is here, and the equilibrium position of this entire system is given this, and now the angle is our theta. So this is the basic figure, okay? And this distance is given to us as 2L sine alpha by 2. Sorry, this angle is alpha, not theta. Okay. So initially it is vertical, and as the dipole is brought together, not together, from infinity close to this charge q, the force of repulsion pushes the charge to a new position, and this position is the equilibrium position, and the height is denoted as h in this case. So obviously, as the charge is being pushed, it is going to gain the potential energy, and there will be also electrostatic potential energy because of the this dipole, and because of the interaction between the dipole and the charge. So we can say that gravitational potential energy which is quite simple because it is raised by the height h, so it will be equal to mgh, and this gravitational potential energy is of charge q, Similarly, we can write electrostatic potential energy between dipole and point charge, and that is our U of E, which will be equal to minus K dipole and Q and suppose this distance is our D, which we can substitute later on. So this becomes D square. So therefore the total work done let us suppose that our W will be equal to, or will be equivalent to, our gravitational potential energy plus we have this as electrostatic potential energy, K PQ upon D square. Okay. And at this particular moment means when it is equilibrium, this charge Q is going to experience our basically three forces. One will be mg in the downward direction, tension along the string because it is tied fixed at this point, and other one will be the electrostatic force due to the dipole. Okay, for that we can just draw the diagram also. We can say that charge experiences three forces. First is our gravitational force. Fg, whichever mg, and acting in downward direction, and then will be tension in the string, and that will be act along the string at an angle alpha. Along the string at angle alpha. And finally, the third one is our electrostatic force due to dipole. Electrostatic force due to dipole, and we can write this Fe, where this value of Fe or equation for Fe will be equal to K PQ upon d cube. And this respective forces we can just draw with the help of figure also, because we have to find out various angles here. And suppose this is the fixed, and we have a vertical initial position, and this is our horizontal, and the final position is our this is charge Q. So we have a dipole P, and we have charge Q here, and this distance we have assumed as d. So we are given this as our alpha. So in the downward direction we are going to have a mg, and there will be tension T along the string. Okay, tension T along the string, and we are going to have electrostatic force, that is our F, and length of the string is given L. So this is also L, and this will be also L. And if we assume that we are having, so suppose this angle will be our alpha, and if we extend it in downward direction, so this angle will be also our alpha, and if this angle is our beta, so we are going to have this angle will be also beta, and this angle will be also our beta. Okay. And similarly for the other side also, vertical opposite angle, so this is our beta, and this is also beta. So because we are going to use the Lem's theorem in order to find out the relationship between all the forces rather. Okay. So we can say our force, our tension T will be equal to sine of the angle between the other two forces, that is our alpha plus beta, will be equal to our force mg, and that will be equal to sine of the angle between the other two forces, that is also alpha plus beta. And then we have our electrostatic force, which is given as 2k one second. I missed something, I think. Here I missed. This is 2. So we get 2k p 2k pq divided by d cube, and sine of the angle between the two is our beta plus beta is our twice beta. And we can write that our we have our, let us call this as O, this as our A, and this point as our B. So in triangle OAB, we can write alpha plus twice beta is equal to 180, and from here we can write our alpha is equal to this will be our, sorry, not alpha but beta. One second. Alpha plus beta is equal to, yes, so we can write that our twice beta is equal to pi minus alpha, and beta okay, so we are going to consider these two parts and try to solve it. So we can write that our mg upon sine of alpha plus beta is equal to, we have this as 2k pq d cube sine of 2 beta, and this can be written as our mg sine of pi by 2 minus alpha by 2, sorry, alpha by 2 and plus alpha, because here we know our beta will be equal to pi by 2 minus alpha by 2. So we are going to use both equation. Here we are going to use first part, we are going to substitute our beta, and in the second part we are going to substitute our twice beta. So this comes as 2k pq d cube, and this will be sine of pi minus alpha, and this portion will be coming as alpha by 2. So we get this as our mg sine of pi by 2 plus alpha by 2 is equal to 2k pq d cube sine of pi minus alpha. Now we can use the trigonometric identity and swap, change the, because of this pi by 2 plus alpha by 2 and pi minus alpha. So this gives us our mg divided by cos of alpha by 2 is equal to 2k pq, and we have this as d cube sine of alpha. Okay, so let us combine the trigonometric function. So we can write this will be equal to our k pq upon d cube is equal to, we get this as sine alpha we get this as our sine of alpha divided by cos of alpha by 2 and multiply by our mg. Okay, and we can just, I forgot one thing, that is our 2. So we can use the half angle, therefore we get that our and let me write this as square and here multiply by d. So we get this as k PQ d square will be equal to, we can write this will be our 2 sine alpha by 2 cos alpha by 2 divided by 2 cos alpha by 2 multiply by mg, and d is already given to us, that is our 2l sine of alpha by 2, and this 2 cos alpha by 2 cos alpha by 2 cancels out, so we get this will be equal to 2l sine square alpha by 2, and we get 2 mgl, and we have this as sine square alpha by 2, and this angle will be also a beta. So from here we can find out the cos of beta. Cos of beta will be equal to h upon d. So you can say our cos of beta is equal to h upon d. D we already is given to us. So let me write it here. Okay. Let me draw the figure first. So this is our horizontal portion. A dipole P is here, which we called as point A. This is point B, which is charge Q, and it is given at height h. So this angle was our beta, this angle was our alpha, this angle was our beta. So we get that this angle will be also beta, and this distance is our d. Therefore we get cos of beta is equal to h upon d, and d is already given to us, that is our twice l sine of alpha by 2, and beta we already know, so we can put this is cos of pi by 2 minus alpha by 2 is equal to h upon 2l sine of alpha by 2, and this will be giving us sine alpha by 2 and sine alpha by 2. So we get this as our sine alpha by 2 is equal to h upon 2l sine alpha by 2. So this gives us sine square alpha by 2 is equal to h upon 2l. And this is our kpq upon d square. Therefore we found out our this sine square alpha by 2. Let us call this equation 1. So we can say from equation 1, we substitute sine square alpha by 2, we get this as kpq upon d square is equal to 2 mgl multiplied by h upon 2l. So here 2 and 2, l and l goes away, so we get this will be equal to mgh. So we simply substitute now our work done, that is our W. So our W, which was equal to our mgh plus, it was equal to kp, sorry, it has to be, one second, yeah, plus K PQ upon d square. So this comes as mgh plus mgh, that is twice mgh, and we are given this as n times mgh. So therefore value of n is equal to 2. So the value of n is equal to 2. Next question. We are given that two identical non-conducting solid spheres of same mass and charge are suspended in air from a common point by two non-conducting massless strings of same length. At equilibrium, the angle between the string is alpha. The spheres are now immersed in a dielectric liquid of density 8000 kg per meter cube and dielectric constant 21. If the angle between the strings remains same after the immersion, then so we have to check which of the following option is correct or incorrect. So basically first two are with respect to the electric forces, third is mass density of the sphere, and the last one is the tension the strings holding remains unchanged. Okay. So we can just divide the question into two parts. First, when the entire system is in the air, so we can just draw the figure. So initially suppose this is the mean position and the charges are the equilibrium are at angle of alpha with respect to the vertical. So these are the two charges and angle is alpha and this angle is also alpha. Angle between string is okay, not alpha but alpha by 2, because between the string is given as alpha. So this will be alpha by 2 and this will be alpha by 2. And so obviously there will be a force of repulsion, that is our force F. In the downward direction we are going to have our mg and there will be tension T along the string. And we are going to have this angle will be also our alpha by 2. So this angle will be also our alpha by 2. And this is our in air. The second case, it is immersed in the liquid. And it says that the angle has to be same. So angle will be over alpha by 2 and alpha by 2. And these are two forces. And let us suppose tension is over T1. Here tension will be over T2. And there will be a force because of, suppose the dielectric constant is our K. So force become our F by K. And the angle it will be our alpha by 2 in the downward direction, because upward there will be buoyant force. So in the downward direction we are going to have net force, that is mg minus our density of the liquid, volume displaced, and multiply by g. Okay. And tension is our T2. So this is our liquid. So first option, that is quite straightforward. That is with respect to electric fields, this electric force is going to remain unchanged. Okay, because it is, you can say, dependent upon the our not on the medium, independent of the medium basically. So option A is straightforward correct. And we are going to check what about the mass density as well as the tension. So now we are going to find out the mass density, that is option C. And we have to remember that the force is F in the air and F by K for the immersed in the liquid, but it is balanced. Okay. So therefore we can say that and angle has to be same. So we can say force is before and after immersion. Force is before and after immersion. So first of all, let us discuss our air. You can say in air we have our electric force, let us call this as F air, and that will be equal to 1 upon 4 pi epsilon naught. Charges are same, so this comes as q square, and the distance between the two is, let us suppose, our r, that comes as r square. And we have a vertical force, that is our mg. Let us call this as our fg. So in the horizontal equilibrium we can just find out the angle directly, because our tension can divide into two components, sine alpha by 2, cos alpha by 2, and let me divide it, then we can discuss it. So this will be our T1, and we have our sine of alpha by 2, this is our T1 cos alpha by 2. So we get that our T1 cos alpha by 2 is equal to mg, and we have our T1 sine alpha by 2 is equal to our F air. So we can say this tangent alpha by 2 will be equal to F air divided by mg. Similarly, we can write for in liquid. In liquid, we can write our electric force if we write this as F liquid will be equal to F air divided by K. And because the buoyant force, we are required to find out the effective weight. So we can see our effective weight due to buoyancy we can write that our W effective will be equal to mg minus density of the liquid, volume displaced, and multiply by g. And mass is our mass of the sphere, which will be our volume of the sphere multiplied by its density, volume. So we can write this as density of the sphere minus density of the liquid multiplied by volume multiplied by g. So once again, similarly, we can write that our tangent of alpha by 2 will be equal to our force of the liquid divided by effective weight W effective. We substitute it, we get this as F air by K divided by density of the sphere minus density of the liquid and volume multiplied by G. Now the angle has to be same. So tangent of alpha, alpha by 2 and tangent of alpha by 2. So we can write for same angle we get F air upon mg is equal to F air upon K divided by density of sphere minus density of the liquid, volume of and multiply by G. So we can easily cancel out our F air as well as G. So this gives us 1 upon m is equal to 1 upon K density of sphere minus density of liquid multiplied by volume. And we can just substitute mass also. So we can write this as 1 upon density of sphere multiplied by volume is equal to 1 upon K density of sphere minus density of the liquid multiplied by volume. And here this volume and volume cancel out. So we are supposed to find out the density of the sphere. And so we can just easily sort it out. So we can write K multiplied by density of sphere minus density of liquid is equal to density of sphere. So we open the bracket, we get density of the sphere multiplied by K minus density of the liquid is equal to density of sphere. So we get that density of sphere is equal to K minus 1 is equal to K density of the liquid. So this gives us density of the sphere is equal to K times density of the liquid divided by K minus 1. This comes as 21 multiplied by 800 and this is about 21 minus 1, which gives us 840. So option C is correct. So we have option A and C are correct. Option A and C are correct. And option D, it states that tension in the string is unchanged. Basically it is asking that our T1 is equal to T2, which is not correct because the tension had to adjust so that our angle is to be same. Okay, because it says that our angle is same. So that's why the tension had to adjust itself, giving us tension, our angle is to be same. Next question. We are given two capacitors with capacitance value C1 is equal to 2000 plus minus 10 picofarad, C2 3000 plus minus 15 picofarad are connected in series. The voltage applied across this combination is V 5 plus minus 0.02 volt. The percentage error in the calculation of the energy stored in this combination of the capacitor is. So we are given that the capacitors are in series and we have to find out the percentage error. So first of all, we are going to find out the equivalent capacitance in the series. Equivalent capacitance, that is our 1 upon C is equal to 1 upon C1 plus 1 upon C2. So this gives us our C is equal to C1 times C2, C1 plus C2, which gives us our 2000 multiplied by 3000 and 2000 plus 3000. So we get our value of C is equal to 1200 picofarad. Now we are going to find out the relative uncertainty or error which is given to us. Relative uncertainty. First of all, we are going to find out it in C1. So for C1, we can write this as delta of C1 upon C1, which is given as 10 upon 2000, and that will be our 0.5%. Similarly, we write for our C2, that is our delta of C2 upon C2, giving us 15 upon 3000, it is 0.5%. And voltage is also, because we require energy, so we can say for V, delta V upon V is equal to 0.02 divided by 5, which gives us 0.4%. And now we are going to find out in terms of C also, okay? Because for energy calculation we require both C as well as V, C equivalent rather, which we have denoted as C. So this is a C equivalent. So we are going to find out relative uncertainty in C. So we can say in C, it is much more easier to use the logarithmic function, and this gives us natural log of C is equal to natural log of C1 plus natural log of C2 and minus natural log of C1 plus C2. So from here we differentiate it with respect to C1, or we can say partial differentiate. So we can write it partial differentiation of natural log of C divided by natural partial differentiation with respect to natural log of C1 is equal to 1, and minus this comes as C1 C2, and this will be C1 upon C1 plus C2, which gives us 1 minus 2000 divided by 5000, giving us 0.6. Similarly, we do a partial derivative for our C2 also, natural log of C2. So this comes as natural partial derivative of our C with respect to natural log of C2, giving us 1 minus, and this will be now C2 upon C1 plus C2, C1 plus C2, giving us 1 minus 3000 divided by 5000, which will be 0.4. Therefore, we can say that our delta C upon C will be equal to, we have this as 0.6 multiplied by 0.005 and plus 0.4 multiplied by 0.005, and this is our first part and this is second part, yeah. And so we get delta C upon C will be equal to 0.005, which will be coming as 0.5%. Now we can easily do it for the energy. So we can say percentage error in energy stored, and the formula is given as E is equal to half CV square. So therefore we can write that our delta E upon E will be equal to delta C upon C plus twice multiplied by delta V upon V. And delta C upon C we found out is 0.005 plus 2 delta V into V found out is our 0.004. So we get this is equal to 0.013, which is giving us 1.3%. So it is coming as 1.3%. So this completes all the 7 questions of advance which were asked in the year 2020. And this was the 4th and final part. So this completes all the questions from the year 2020, mains as well as advance. In the first 3 part we covered the mains question, and this is the 4th part in which we covered all the advanced questions. This completes 2020. Thank you.